Hello, students. So let me set the stage for what this document is. You'll recall that we didn't finish all the applications of exponential and logarithmic functions that I wanted to do on Wednesday, I guess, Tuesday. So what am I doing right now? I'm standing in our usual classroom, which is completely empty. There it is. Talking to myself while recording myself using the document camera. And my goal is just to finish up these examples about interest rates, take a look at this video, and then there's the homework that has been posted as bonus homework on the web page that will be related to it that you should think about. Shadow is going to be there the whole time, and it'll be there. So here's the game. Let's suppose you put $5 in a bank account which has an annual interest rate of 10% compounded once a year. This is obviously a ridiculous situation. Where are you going to find a bank account that has an annual interest rate of 10%? You won't. And where are you going to find a bank account that has any interest rate that lets you put in only $5? You won't. So it's a made-up example. After 1 year, then you'll have the original $5, and then you'll have that extra 10% interest on $5. So you'll have $5 plus 10% of $5, so you'll have 5 times 1 plus 10%. 10% is 0.1, so it'll be 5 times 1.1, or 550. I guess dollars are usually measured out accurate to the cents place. So after another year, what will you do if you just leave it in that account? Well, you'll have that original 10% interest, and then you'll get 10% interest on that total. So you'll multiply by 1.1 twice. So after 2 years, you'll have 5 times $1.1, which, by the magic of television, I've done all the computations in advance. So you have a total of $6.05. So maybe a thing worth noticing is autofocus. Hopefully that's better. If you put it in for 2 years, you have more than twice the amount that you have when you put it in for only 1. I don't know if you can hear that, but I'm going to go shut it off. Nice. How much will you have after 10 years? Well, what will that mean? Well, to figure out how much you should have, well, you start with the $5, and then you multiply by 1.1 10 times, 1.1 to the 10th. Again, by the magic of television, I've pre-computed all of these. As I go through this document, you should absolutely pause the video an awful lot and do a lot of the computations in advance. You end up with $12.97. In fact, there are more digits after that decimal place. I'll round everything to the nearest penny. So, cool. So that's how to compute interest if you have a bank account that has a fixed annual interest rate that's compounded once at the end of the year. So it sits in there for a full year and then gets its 10% interest at the end of the year. So let's suppose a bank advertises the same annual interest rate of 10%, but it compounds that interest rate quarterly. So what will that mean? That means every quarter of a year, every 3 months, the bank will treat your account as if it has gained 10% interest, but not 10% interest, only a quarter of 10% interest. You'll get 10% divided by 4 interest, so 2.5% interest every quarter of a year. Let's see if that makes a difference. So that means after 1 year, you'll wind up taking the initial investment, the principal, $5, and multiply by 1.025 4 times. Again, by the magic of television. That's $5.52. And you'll notice that's more money. So here's an interesting observation. Even if you have the same annual interest rate, compounded more frequently, the resulting interest will be greater than if you just compounded once a year. If you compound more times per year, even if the annual interest rate is the same, there's a higher effective annual interest rate. In 2 years, you'll wind up multiplying by 1.025. Well, 2 times 4 is 8, so 8 times. You do that, you wind up with approximately $6.09, which again, notice, that's 4 cents more than you would have had if you just compounded once a year. If you wait 10 years, you'll have 5 times 1.025 raised to the, how many times do you multiply by 4? Well, in 10 years, if you multiply 4 times every year, that'll be 4 times 10, or 40 times. Nice, so you wind up with more money, again, than if you just compound once a year. There's a general formula at play here. If you have some initial investment P, called the principal, which you put in an account with an annual interest rate of R, and you compound that interest rate n times per year, so above n was 4, then the amount, which I'll call A, in the account after T years is, well, probably it should be something times the initial principal, right? If you invest more money, you should wind up with more at the end. That's a typo. The amount at the end of your time period is given by 1 plus the interest rate divided by n. So if you like, that's the interest rate annually, but you do it n times, so you treat it as if the interest rate is 1/nth what it was, but you do it n times, so it should come out in the wash. And then you raise that to the power of, well, how many times do you compound your interest? Well, it's n times per year if you wait t years, and you get n times t applications of your interest. Nice. So let's use this formula. So let's suppose you put $150, so that's your principal, in an account with an annual interest rate of 10%, also known as 0.1. So there's R, compounded monthly. So you compound 12 times per year, so n is equal to 12. Let's figure out how much will be in the account after 10 years. So it's the A of, after 10 years, so A of 10 will be $150, that's the principal, times 1 plus R, 0.1, divided by 12, raised to the, n is 12 times 10. And obviously that's not something that I'm going to want to do by hand. Right? I could compute what 0.1 over 12 is. That would be fine. I could even add 1 to it easily enough. But then I need to multiply that by itself 120 times. I'm not going to do that by hand. In fact, a computer wouldn't do that way. A computer will do some logarithm magic to compute it. Using that computer, though, you end up with approximately $406.06. Let's take that exact same situation and take that interest rate and compound it every day. So, right, this is slightly dishonest. There aren't exactly 365 days in a year, but let's say there are 365 days in a year. Then you'll get A of 10 is the initial investment, the principal, 150, times 1 plus R, which is still 0.1, divided by n, 365, raised to the 10 times 365. And I'll do all of the approximations at the end. So let's say instead of compounding 365 times, you say, well, it would be even better if I compounded this interest more times. So let's see what happens if we compound the interest 10,000 times per year. So I guess that's like, what, 30 times every day, give or take? A of 10 is 150 times 1 plus 0.1 divided by 10,000 raised to the 10 times 10,000. and I'm definitely not going to do that by hand. If you compound 100,000 times in a year, so I guess that's like, I don't know, 300 times a day, you'll get a of 10 to be 150 times 1 plus 0.1 divided by 100,000 raised to the 10 times 100,000. So I guess I know that that's a million. Let's see what this works out as. So you should pause for a moment, do each of these computations. I will now just write down what the result is. 407.68643, and I know I'm writing out more decimal places than you would see in a money account. That's okay. If you compound 10,000 times per year, you get $407.74023. So you notice to go from this to there, it like improves in the dollars place. So that was just going from 12 to 365. 365 to 10,000, that seems like an even bigger jump, but it's only changed in the tens of cents place. To go from 10,000 to 100,000, it improved by less than a penny. So what's the point here? We see that whenever we increase the number of times we compound per year, the interest rate is effectively better. We're getting more money at the end of the same amount of time. But it looks like the improvement is trailing off. Even though here we improved from 10,000 to 100,000, that seems like a lot. In 10 years, it made less than a penny difference. So that suggests something. That suggests that maybe there's like a best we can possibly do, no matter how many times we improve the interest rate. Oh dear. I think that was quite possibly just not in page for that whole time. You have the picture now. I guess you can play the audio over it. I don't know. This is suggestive that maybe there's a best we can possibly do, no matter how many times we compound the interest. There's an upper bound on how big a difference it will make. And there is. In fact, we get the following formula. So if you put some initial principal P in a continuously compounding interest-bearing account with interest rate error for n years, so this is like, we're putting this for t years. T should be time. So this is like n equal to infinity. I'm going to compound it absolutely every moment. Then I'll get the formula that the amount in the account after t years is P times Euler's number, E, raised to the error times t. Now it might seem strange that Euler's number should show up, but the following example will demonstrate that Euler's number should show up, that this is the right thing. And we'll do it by doing some computations. Let's suppose I put $100 in an account with an annual interest rate of 5%, also known as 0.05, compounded either annually, 5 times per year, 24 times per year, 365 times per year, 100,000 times per year, or continuously. In fact, I think I'll do more than that. Let's also compound it 1,000,000 times per year and 10 million times per year. And we'll see what we get each time. So let's go ahead and do it. So I've put P equal to $100, so P is 100. I'm putting it in for 5 years, so T is 5. I'll point out this typo again. That N in the superscript should actually just be a T. T equals 5. In this first example, well, no, in all of these examples, R is 0.05, and N is 1. So if nope, that only applies to this example. I'll compound once per year. Then the formula is the initial principal Well, let's write it down. So the amount after t years, p times 1 plus r over n raised to the t multiplied by n. So what do we get? We have 100 times 1 plus 0.05 raised to the t. Nice. And you can go ahead and do that computation. I'll just write down the result. 127.62816. And it's in dollars. All of this is in dollars. If you compound 5 times per year, you get $100 times 1 plus 0.5 divided by 5 raised to the 5 times 5. Compounding 24 times per year, 100 times 1 plus 0.05 divided by 24 raised to the 5 multiplied by 24. Maybe you know that that's 600. I think it's 600, but I won't bother doing anything by hand. 100 times 1 plus 0.05 divided by 365 raised to the 5 times 365. 100 times 1 plus 0.05 divided by 100,000 raised to the 5 times 100,000. And I won't even write the formulas down for the next two. Let's just write down the approximations. So what you should do right now is, on your own, find your calculator, find the Google calculator, I don't care. Evaluate these expressions. Be careful with parentheses, right? You need parentheses around those if you're entering it in a machine, otherwise it will raise to the 5th power, then multiply by 5. So let's write it all out. So I'm trying to write it so that the digits line up. I'll probably screw up, but I'll do my best. 128.40253, 128 point. And I haven't even written the formula down, but I'll write down what it works out to be approximately. 128.40. No, I've screwed up. Compounding 5 times per year. You know what? There we go. Let's just use my pre-written thing instead of, because all I was doing was copying down. Compounding once per year was $127.62.816. Compounding 5 times per year, $128.2432. 24 times gave us $128.36915. 128.40032. 128.40253. 1 million times 128.40254, 10 million times 128.40254, and something else at the end. So let's just do a quick bit of analysis of the digits. So when we went from once per year to 5 times per year, we found a difference in the pennies place. Nope, in the dollars place. That's nice. When we went from 5 times per year to 24 times per year, that seems like a big jump, but we saw a difference of tens of cents, 12 cents-ish. To go from 24 to 365 times, well, it's still that digit that changed, but this was like a 4-cent improvement. From 365 times to 100,000 times, that was less than a 1 penny improvement. We improved our situation by like 0.2 cents. To go from 100,000 times to 1 million times, the difference was in the, let's see, dimes, pennies, tenths of pennies, hundredths of pennies, thousandths of pennies. we improved our payoff by about 1/1000th of a penny. When we compounded interest 10 million times per year, well, we didn't even see a difference. So this is suggestive that, well, it's stabilizing. No matter how many times we compound our interest per year after 5 years, we're not going to do much better than this. If we compound interest continuously, what's the formula? The formula is P times E to the R T. So that's P equal to 100, E Euler's number, raised to the R, 0.5 times T. Plug that into a machine. Yep, you get 128.40254. In fact, the difference between these two, you can go and compute it yourself, they'll differ only after 7 digits after the decimal place. So these two numbers are really close. So indeed, this formula for computing continuously compounding interest seems complicated and weird, but in fact, it's just what it should be. Nice. So ideally, this will solve as something that'll be helpful for those of you who are doing the bonus homework. Some of you have already turned it in, which is interesting. I hope you've enjoyed it. I will see you in class tomorrow, though if you don't watch this the same day as I record it, your results may differ. Talk to you later.